So erase all this. And this, but we retain the form of the solution. We're going to look for a power series solution again, but this time, instead of having the epsilon, the small parameter, multiplying the first derivative, it's going to multiply the second derivative. Epsilon over here. All right. Same thing as before. We substitute the power series into the equation and collect the like terms to see what we get. All right. So plugging in and collecting terms to epsilon to the power 0, what do we get? So we will get nothing from the second derivative because there's an epsilon out front, but we'll get a term for y naught primed of x from this term in here, and minus 1 equals 0 from that one. And then the boundary conditions will be y naught of 0 equals 0, y naught of 1 equals 2. And then we can collect the next order, epsilon to the power 1. And now we'll get the second derivative of y naught as a term times epsilon. So we'll have y naught double primed of x plus y1 primed of x equals 0. And this one doesn't have anything involving epsilon. And then the boundary conditions, which are y1 of x, sorry, y1 of 0 equals 0, and y2, sorry, and y1 of 1 equals 0. Right, so this one satisfied the 2, and then next one, next order, the boundary conditions are homogeneous. And we can keep going in principle. All right, so now let's solve the first problem. So what we get is y naught primed is equal to minus 1, or y naught is equal to minus x plus a constant c. No, plus y naught prime equals 1, and y naught is the x plus c. And now, so we have one arbitrary constant, but we have two boundary conditions. So clearly, we're not going to be able to solve both of them, right? If we try to plug in at 0, x equals 0, then that would mean c is 0. But if c is 0, then y naught of 1 is going to be equal to 1, not 2. On the other hand, if we try to satisfy the boundary condition at 2, we get 1 plus c is equal to 2, or c is equal to 1. And if c is 1, then when I plug in 0, I get y naught of 0 is equal to 1, not 0. Right? So we cannot satisfy both boundary conditions. So this is an example where, as before, where we dropped the y squared term in the quadratic because it was thought to be small because it multiplied in epsilon. We have the same kind of business here, where if epsilon is small, it seems that we should be able to drop this term, but if we drop the term, then we can satisfy only one of the two boundary conditions. So clearly, if we're going to satisfy both boundary conditions, this term here, involving a second derivative, has to become big at some place in the domain, such that it's big enough that it will swamp or balance the epsilon, which is going to 0. This one has to become big. Right? So someplace the second derivative has to be big. And we can imagine it happening at two places. We can keep the solution saying that that's valid at y naught of 1 equals 2, and then assume that something different happens when we get close to 0. When we get close to 0, somehow this term, which is negligible everywhere except close to 0, becomes important. Or we can do the alternative case where we are going to satisfy this boundary condition and assume that something different happens when we get close to x equals 1. So this time we're going to first assume that this solution is valid everywhere away from x equals 0, and that close to x equals 0, something else happened. We get what's called a boundary layer, which is the point of this. Okay, so let's retain this solution here. This one is going to be called the interior solution. So y naught of x is equal to x plus c is the interior solution, which means that c, we'll use it to satisfy the boundary condition at y naught of 1 equals 2. So by the interior we mean, sorry, the interior solution away from x equals 0. So at x equals 0, we're going to have a boundary layer where this term will have to become important, even though it's multiplied by epsilon, which is a small number. But away from x equals 0, then this is the Basler solution. So if this is valid away from x equals 0, then it has to satisfy the boundary condition at x equals 1. So that means that c is equal to 1. And so my solution is really just x plus 1, right? Okay, and now we have to do something different when we get close to x equals 0. And I'm not going to bother solving the other orders, but one could do it. Okay, so if the second derivative is becoming important, we can imagine rescaling the x such that when we do the derivative and we apply the product rule, we're going to come out with, sorry, not the product rule, the chain rule, we will get terms that involve some functions of epsilon. And so what we will try to do is close to x equals 0, we're going to come up with a new rescale variable. We introduce a stretched variable. Oh, and it will be x tilde is equal to the old x divided by epsilon to the power a. And we don't know yet what that power of a is. We'll determine it shortly. But the point is, as epsilon goes to 0, this x will vary very rapidly, right? A small change in x will imply a big change in x tilde. So that means that x tilde will be able to resolve nicely what happens close to the boundary at x equals 0. All right, if we do that, then we say that y of x is going to be a new y tilde of x tilde. And if we take the chain rule and take the derivatives, y primed of x is equal to dy tilde dx tilde dx tilde dx, and that's equal to dx tilde dx is just epsilon to the minus a times y tilde primed, right, of x tilde. So dx tilde dx gives me a factor of 1 over epsilon to the a. And similarly, if we try to get that the second derivative, y double prime of x is going to be, and now we take the derivative of this, so it'll be epsilon to the minus a dy tilde prime dx tilde dx tilde dx. And that's going to be, we'll get another factor of epsilon to the minus a, so we get epsilon to the minus 2a times y tilde double primed of x tilde. And so the solution we're going to look for is going to be in the boundary layer will be of this form. Y tilde of x is going to be equal to y naught tilde of x tilde, there's a tilde here, plus epsilon y tilde 1 of x tilde plus dot dot dot. So we're going to look for that form of a solution. And then we're going to substitute this into the equation and see what we get. All right, so I need more space. So remember, we're going to look for a solution of this form. I need to record this somewhere. And I need to remember that y primed is equal to epsilon to the minus a y tilde prime, and y double primed is equal to epsilon to the minus 2a y tilde double prime. So I need that. I can't erase it. And I also need to know to record what the interior solution, the solution away from the boundary is. Okay, so I want to keep the problem. And I know that away from x equals 0, y naught of x, or y of x, is equal to y naught of x plus epsilon dot 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 dot, y y1 of x plus, and that's equal to 1 plus x, right? I got x plus 1 plus epsilon times something, which I didn't solve, plus dot dot dot. And now we go to close to x equals 0. So close to x equals 0. What do we have? So close to x equals 0, the problem I will have will be epsilon. And just like before, like we did with the quadratic equation with these funny powers of 8, we're going to plug in what we have, this term here, times epsilon to the minus 2a y tilde naught double prime plus more terms plus epsilon to the minus a y tilde naught primed plus more terms minus 1 equals 0. And now we're ready again to apply the method of dominant balance. So if I erase all this here, right, we have different possibilities. I kept only the biggest of the terms in the long series, right? There's going to be more terms, but this one, close to x equals 0, is going to be bigger than all the other terms. Right, because when we multiply by epsilon, like the next one will have an epsilon to the minus 2a minus 1. And so we can have different balances. So case 1, I guess, is this balance, right? Maybe this term balances this one, case 1, and this one is small compared to the other two. Case 2 would be this one balances this one, case 2. And both of these are bigger than the one. And then case 3 would be the first term balances the third term, the last term, case 3. And we can investigate each of these terms, each of these potential balances in term, and see if they're consistent or not. So let's start off with case 1. Case 1, that means that epsilon to the minus a y tilde naught prime minus 1 equals 0. And if this is going to be true for any epsilon, then a has to be 0, right? That implies that a equals 0. And if a equals 0, then our leading order problem is just y naught prime tilde minus 1 equals 0. And that returns the same solution we had over here, right? Did I copy it? Yeah. Right, this is going to give back this solution, the same problem we had before, which is not the right balance close to the boundary layer. So this is not the one we want. We don't want to balance these two terms. That's what we had before. And so let's try case 2. Case 2, that's where these two terms balance. So then I'll have epsilon to the minus 2a plus 1 y tilde naught double prime plus epsilon to the minus a y tilde naught prime equals 0. And if that's the case, then minus 2a plus 1 is equal to minus a, or 1 is equal to a, right? A is equal to 1. And so then the problem boils down to y naught tilde double primed plus y tilde naught prime equals 0. And we can now solve this problem. If we solve this problem, what do we get? All right, so if a is equal to 1, this becomes our equation. And so we're going to look for a solution of the form y naught tilde is equal to some constant a e to the lambda x tilde. We substitute into the equation, we get lambda squared times a times e to the lambda x tilde plus lambda times a e to the lambda x tilde equals 0. These terms cancel. And so we're left with lambda squared plus lambda is equal to 0, which implies that either lambda equals 0 or lambda is equal to minus 1. So the solution to the first order problem is y naught tilde of x tilde is equal to if lambda is 0, that's just a constant. So we have c1 plus c2 e to the minus x tilde. And remember, x tilde is just x over epsilon to the power a, and a is 1. So now this, if I go back to the original variable, I get y naught of x. All right, so this is the first term in the power series in the boundary layer. And now we want to satisfy the boundary conditions, right? So the boundary conditions at y of 0 equals 0, that implies that if I plug in 0, I should get 0. So that means y of 0 equals 0 implies that c1 plus c2 equals 0, or c1 is equal to minus c2. Right? So that means the solution is c1 times 1 minus e to the minus x over epsilon. Now this satisfies the boundary condition at x equals 0. What happens away when we move away from x equals 0? Well, eventually we're going to, as we go away from x equals 0, we want this solution to match this solution, the one we got from the part away from the boundary condition, right? We want y naught of x in the boundary layer close to x equals 0 to approach, or to match, I guess, to match y naught of x away from the boundary layer as x goes to infinity. In other words, or maybe as the stretch variable, right? As the stretch variable moves away from the boundary, we want this solution to approach this solution, so it'll be continuous. And so that allows us, that matching is going to allow us to find out what y c1 is. So let's see. So in the limit as x goes to infinity, or as x tilde goes to infinity, this term here will vanish, right? Because it'll be e to the minus infinity. And so this y naught in the boundary layer, the limit as x goes to infinity of this term is equal to just c1. And whereas this one, as I go towards x equals 0, this one is just equal to 1, right? So that means that c1 has to be equal to 1. And so now I have a solution for the boundary layer, which is 1 minus e to the minus x over epsilon. I have a solution away from the boundary layer, which is just x plus 1. And if I want to piece them together, well, there's going to be a double counting as I move away from x equals 0, this solution is going to be equal to 1. And similarly, this one, as I move towards x equals 0, this one also is equal to 1. So there's going to be a double counting. So if I want the solution to be uniformly valid, what I do is I add this solution plus this solution, and I subtract off the common part. So the uniformly valid solution is this one. So 2 order epsilon, right? So the order epsilon to the power 0, solution is going to be this solution, y naught of x is equal to x plus 1. That's the solution away from x equals 0, plus the solution that I just erased, which is 1 minus e to the minus x over epsilon. This is the solution close to, or the boundary layer solution. And then I subtract the common part, which is minus 1. And now this is going to be valid everywhere to order epsilon, right? So let's check that it satisfies the boundary condition. If I plug in x equals 0, what I have is 1 plus 1 minus 1, which is 0, minus 1, so 1 minus 1, and I get 0. So it satisfies the boundary condition at x equals 0. At x equals 1, what I have is 1 plus 1 is 2, plus 1 minus 1, so yeah, at x, as I approach x equals 1 and epsilon goes to 0, this term here vanishes, right? So if I go close to x equals 1, this term vanishes, so I get 1 plus 1 is 2, plus 1, this term vanishes, minus 1, and vanishes, so I get 2. This term also. So it also satisfies the boundary condition. And if I'm away from the boundary layer, if I'm out in the middle, this term vanishes, right? As x moves away from 0, this term vanishes, and I get 1 minus 1. So this vanishes, and I get back the right solution I had for the interior. And if I get close to the boundary, as x goes to 0, this one goes to 0, so I get 1 minus 1, and this vanishes, and I'm left only with this close to the boundary layer. And so that is how we solve a boundary layer method, solve the problem. Remember I said that we didn't really know if the boundary layer would be at x equals 0 or at x equals 1, right? So what we could do to find out is we can test the other possibility. So if we guess that the boundary layer is at x equals 1, then the interior solution, y naught, is going to be equal to x plus c, which implies that c equals 0, so the interior solution is just y naught equals x. That would be the analog of this solution. And we then introduce a stretch variable, which is going to be valid close to x equals 1. So then we have x tilde is equal to x minus 1 over epsilon to the power a. But it turns out that we know a is equal to 1 from our previous analysis. We just shift it over so that it applies that this number is small when we're close to 1 instead of when we're close to 0. And now if we go through the analysis and we try to solve the solution, what we will get is we'll be able to find the solution to order epsilon to the power 0. We'll be able to satisfy the boundary condition at x equals 1. But if you carry through the analysis, what you'll find is that in the limit when x goes off into the interior towards minus infinity, away from the boundary at x equals 1, the solution, the boundary relationship will blow up instead of decaying the way this one did. And it will not be possible to match this solution with the boundary layer solution. They will not match. And so in that case, you'll get a contradiction or an inconsistency, which means that it was correct all along to apply the boundary layer, retain this term, close to x equals 0. So this becomes important where close to x equals 0, and becomes unimportant as we move away from x equals 0. If I had changed the sign, if this had been a minus here, epsilon y double prime x minus y prime of x, then the boundary layer would have been close to x equals 1 instead. And then we would have done a similar analysis, but with the minus here instead, the boundary layer would have changed location. So the form of the solution in the end is going to look something like this. This is x, and this is y, and I'm going to try to sketch what the solution to order epsilon to the power 0 is. Right, so we know that away from, so forget about this solution, which was wrong. I just want to sketch this one here. So this is the solution which can be valid almost everywhere, except in a very thin layer over here. So this is x equals 0, here is x equals 1, and there's going to be a little layer over here, right, a boundary layer. And so at x equals 1, this starts at 2, so if this is 1, better. So over here, this x plus 1 just becomes over here somewhere, 2. And then it increases from x equals 1 close to 0, so something like this, goes up. And then as we approach x equals 0, this part and this part of the solution vanish, and we're left with this part of the solution. And so now this term here will have to become important close to the boundary, and it has to curve back down to satisfy the boundary condition that y0 of 0 is equal to 0. And so this bit over here, this is the boundary layer over here. And out here, we have the interior solution, which in this case is very simple. It's just a linear increasing function. All right, so that's a brief summary of what perturbation methods are for boundary layer value problems, boundary layer methods. And we're going to use those to think about the Ekman layer in a little bit.